Okay, so to informally state a theorem that we talked about a little bit earlier, if a sequence AN is bounded above, then it converges to what? Its least upper bound. If it's bounded below, if I left out the word monotone, let me go ahead and add that again. An increasing sequence bounded above converges to the least upper bound of the sequence. A decreasing sequence that is bounded below converges to the greatest lower bound of the sequence. Greatest lower bound being the infimum. Okay, let's take a look at our next theorem. It uses the term accumulation point, so let's make sure we remember what an accumulation point of a set is. An accumulation point of a set doesn't have to be in the set, but every little epsilon neighborhood around it contains infinitely many elements of the set. In this case, we're using the set A. So if you're an accumulation, or if a number is an accumulation point of the set A, that means if I go from that accumulation point, that number, plus or minus any epsilon, I'm going to get infinitely many elements of the sequence, of the set, sorry. So here's the theorem. Let A be any subset of the real numbers. The point x0 or x0 is an accumulation point of that set, A, not E, if and only if there is a sequence of numbers where all of the numbers of the sequence are chosen to be in E, but different from x0. Because remember, x0 doesn't even have to be in the set A. For all in the natural numbers, and xn converges to x0. So essentially, you're just finding a sequence of elements in this set that, in this set, and not including x0, that converges to x0. So before we go through the proof, let's do a couple of little examples here. Well, we've seen these before. We know that both 0 and 1 are accumulation points of, I'll use E this time, of this set. That's the interval of numbers strictly in between 0 and 1. And based upon this theorem, we can find a sequence that converges to both 0 and to 1. Here is a sequence made up of elements only in the set E that converge to 0, which is not E, not in E. So therefore, 0 is an accumulation point of the set E. And how can we get one that converges to 1? Any idea?
1.
Say again? You were probably going to say the right thing.
I was going to say 1 plus 1 minus that.
Yeah, 1 minus 1 over n. 1 minus 1 over n is a sequence of terms that are, oh, let me see. Actually, I didn't. 0 is not in that. So how about 1 over that? Otherwise, the first term of this sequence would be 0, and 0 is not in the set E. So if I make it n plus 1, so we start off, the first element is 1 minus a half, then 1 minus a third, 1 minus a fourth, 1 minus a fifth. That converges to 1. And 0 and 1 are accumulation points, and so is 1/2. I wrote up a sequence here. And I could use something like that same flavor there. I'm going to put n minus 1 over 2n. That converges to 1/2. We've seen a sequence that looks something like this, if not exactly this. Without that minus 1 on top, you end up with exactly 1/2. So as n goes to infinity, yeah, there are several ways we could prove this, but I think we can all see that that converges to 1/2. So all three of those points are accumulation points. And I think we looked at this example a couple weeks back. It's, in fact, every single element in the closed interval from 0 to 1 would be an accumulation point of the set E in this example. Okay, I'm going to go through the proof now, and you're going to have to remind me, because actually in my notes I used capital E instead of capital A, so just remind me every time I write down capital E. Okay, the proof of theorem 1.17. All right, this is a bidirectional proof, so we're going to go from left to right the first time. Here's the if and only if. So we're going to assume that x naught is an accumulation point of A, and we will prove that there is a sequence of elements taken out of this set that converges to x0. All right, so we're going this direction first. If x0 is an accumulation point of the set A, then for every n in the natural numbers, there exists an xn that's in E A. I intended actually, I could say A minus x naught, but we'll see how I can get away without writing that in just a second. Such that if x naught is an accumulation point for the set A, then for every n in the natural numbers, I can choose an xn in the set A such that this is true. Well, I want this to be not equal to x0. That's why I could have put minus x0, but why don't I have to do that? Because of what follows, right? I said, I added this part. 0 is less than this. That means that xn can't be equal to x naught. So it's just another way of saying that. I could have taken that off if I would have said xn is an element of A minus x naught. Okay. We now will show that xn converges to x naught. And as we always have to, let epsilon greater than 0 be given. We're going to choose a capital N in the natural numbers such that, and this is something we've done before, I want n to be big, at least relatively speaking. If epsilon is small, I want n to be very, very big. And what does that mean? That means that 1 over capital N is less than epsilon. This is just rephrasing that. They mean the same thing. So based upon that n, we can see that n, little n, greater than capital N implies that the distance between x0 and x naught is less than 1 over n, which is less than or equal to 1 over capital N, and that's strictly less than epsilon. that was easy by our choice of capital N. All right, now we're going to go the other direction. We're going to assume the right-hand side is true. Where's the if and only if here? So we're going to assume that there exists a sequence where every element of the sequence is taken out of A minus X naught, and Xn converges to X naught. And we're going to prove that X naught is an accumulation point. So suppose that Xn is such that Xn is an element of A minus X naught for all natural numbers. So every element is in A, but it's different from X naught. And Xn converges to X naught. So we just need to show that X naught is an accumulation point. All right, so for some arbitrary epsilon greater than 0, let this interval X naught minus epsilon, X naught plus epsilon be a neighborhood of X naught. Well, it remains only to show that that interval has an infinite number of elements. And that would make it an accumulation point for X naught. And to do that, we'll let capital N be such that little n greater than capital N implies that Xn minus X naught is less than epsilon. And we know that capital N exists because Xn converges to X naught. I'll write that down. Possible since Xn converges to X naught. That's an optional comment. To finish this off, therefore, the set of elements, or you could consider it a sequence if you want to, but the set of elements, X capital N plus 1, X capital N plus 2, for all time and evermore, fall in that interval, which means they fall that there's an infinite number of points in that neighborhood. That's the end of the proof. I'm just going to put a little comment down here. It's an infinite number of points. And that's the end of section 1.4 and the end of chapter 1.